Hello, this is Ryan Woodward recording for Intel's Digital Logic course. This is Lab 3 Part 1. And I've already uploaded a video for this, but I was not happy with it, admittedly, and so that's why I'm actually going to take that video down and share this one. Previously in that video I mentioned that I had some issues getting Intel's code in their lab document, or FPGA Academy's code, up and running. For whatever reason, it would not work on my version of Quartus, and so I decided to write my own SR latch code. And that's what I've done here, but at the same time, I wanted to show the specific the gated SR latch that we had to do. And we'll see that this code may allow us to actually build the circuit in Part 3, Part 2. And so that's why I wanted to redo Part 1 to show this circuit, the SR latch, and the extended part to actually be a gated SR latch. There's not much difference between the two, at least off of a video by All About Electronics. They are a fantastic channel. Firstly, I've learned a ton by watching much of their content, and so shout out to them. They're awesome. But here is actually a couple images from their channel. There's a video comparing the gated SR latch and the SR latch itself. On the left here, this is the circuit diagram for an SR latch, and then on the right is the gated SR latch. And so these are the differences. We basically add two AND gates and an enable input, or sometimes called clock. But for me, I just kept as enabled, and I basically made this using the data flow model in VHDL. So for the SR latch, as we can see, we have two NAND gates, or excuse me, NOR gates. That's an OR, and with the not at the end there, so it's a NOR. And we can see that from Q, I just named it Q and Q bar. As we can see on the right here, they have this inverted a bit, so I assumed that Q and Q bar corresponded to similarly here. What we can see is that Q bar, or excuse me, Q, which is this A right here rather than B, it is knotted, or NORed rather. S and B are NORed together. So that would be Q bar in this instance is NORed with S, and that's how we get Q. And in reverse, we have Q bar being R NORed with Q. And so that's what we see for our circuit there. And then for the gated SR latch, we added an enable here at the beginning compared to over here where we just have the 4 inputs and 2 inputs, 2 outputs. We added an extra input for our enable, and then I created a port map of using the SR latch code from the previous file. And we can see that we pass in S and E, R and E to where S and R would be in for the SR latch. Looking at the photo again, we can see that we've got we have the two ANDs, S and enable and R and enable, specifically going into S and R respectively. All right, and that's the code. Essentially, the truth tables would show that, at least for the SR latch, that if we flip R high, we'll see Q bar go high. If we flip S high and R is low, then we'll see Q go high. And that's kind of that flip-flop action we'll see. And for both of these circuits, the SR latch and the gated SR latch, if all the inputs are 1, that is an invalid input, so we will see the LEDs go low. And I will actually demo both of these circuits specifically at the end of this video. Alright, and this is a redo of Lab 3 Part 1, because I wasn't sure the difference between an SR latch and a gated SR latch. And so with this SR latch, there's no enable, and that's key. There's also no clock in this instance, but so we have S and R on these two switches, and then Q and Q bar on the default to these LEDs on the far right there. Here, I'll move it a little bit better. And so we essentially will see this get switched back and forth with the move of these two switches. The only invalid input is if both S and R are high. That's an invalid input. If they are both low, we should see Q be high. And then if we toggle S, we'll see Q bar go high, and then the reverse for if we flip SR. So that's essentially it for our SR latch. And if both are 0, that's what holds the memory at that state. And if I were to clock it, essentially if I were to set a clock for this, we'd see that this LED would not switch back to LED 0 when these two switches are low, even if we clocked it. And we would get an output like this, where both LEDs are low, if both switches are high, even though it would be clocked in that instance. All right, that is the SR latch. Next is the gated SR latch. All right, this is the SR gated latch, or the gated SR latch, sometimes called the clocked SR latch. And that's because the enable is often what is referred to as the clock in that input, but our enable is this third switch from the right here. I've mixed this up, but we have Q, then Q bar is LED R1, as you can see there on the LEDs. So what we can actually do is enable this by switching E, our input, to high, and now we'll actually be able to observe the switching of Q to Q bar and back using S and R. Now, if we were to flip R high with E, then we'll see Q bar go high, and we do. As I said in the previous video, I had these actually Q and Q bar in the previous demo, but now it's flipped. This is Q bar and LED R1, and LED R0 is Q. And the reverse, if we were to flip S high, we'll see Q go high here. And that's that effect with the enable. We can actually flip-flop that. That's why it's actually called a flip-flop at times. And again, the same for the SR latch and the gated SR latch. If all inputs are 1, we have an invalid input, and Q bar will be 0, according to our truth table. But that's it for the gated SR latch.